On a clear night, far from city lights. If you know exactly where to look in the constellation Andromeda, you can see it without a telescope. A faint smudge, barely visible, smaller than the width of your thumb held at arm's length. It does not look like much. What you are actually looking at is a spiral galaxy containing roughly 1 trillion stars, more than the Milky Way, by most estimates, perhaps 2 to 3 times more. A structure more than 200,000 light-years across, roughly twice the diameter of the Milky Way's main disk. The light arriving at your eye right now left that galaxy approximately 5 million years ago, before our species existed, before the ice ages, before anything recognizably human had yet appeared on this planet. And it is moving toward us at roughly 110 kilometers per second. That is the speed at which the center of the Andromeda galaxy is approaching the center of the Milky Way right now, tonight, while you are looking at that smudge in the sky. 110 kilometers per second, nearly 400,000 kilometers per hour. In the time it takes you to finish watching this video, Andromeda will have moved several million kilometers closer. For decades, astronomers have described what this means in the same terms. In approximately 5 billion years, Andromeda and the Milky Way will collide. The two largest galaxies in the local group, the small cluster of galaxies that constitutes our cosmic neighborhood, will meet, pass through each other, swing around, meet again, and eventually merge into a single new galaxy. Spiral arms will be torn apart, stars will be scattered into new orbits. The night sky, as seen from whatever remains of Earth's solar system, will be transformed beyond recognition. This is the story most videos about this event tell. It is not wrong. It describes a genuine possibility, well supported by the physics we understand, consistent with what we see happening in other pairs of galaxies scattered across the observable universe. The problem is that it is presented as settled, as the expected outcome, when the underlying scientific picture has become considerably more complicated in the past year. What seemed like a confident prediction is, in mid-2026, better described as the L-eating hypothesis in an ongoing measurement debate. Then, in June 2025, a team of researchers published a paper in Nature Astronomy that changed the terms of the conversation. Using the latest data from the European Space Agency's Gaia satellite and the Hubble Space Telescope, running 100,000 simulations of how the Milky Way, Andromeda, and their companion galaxies might evolve over the next 10 billion years, they found something unexpected. When all the relevant gravitational influences were included, particularly the orbit of the Large Magellanic Cloud, a satellite galaxy of the Milky Way whose presence complicates the trajectory in ways earlier models had underestimated, the probability that the Milky Way and Andromeda will actually merge drops to roughly 50%. A coin flip. 9 months later, in March 2026, a different team published a counter-analysis using the same Gaia data, but with more precisely corrected measurements, adjusted for specific systematic errors in how Gaia measures the motion of stars in Andromeda. Their result: the merger probability rises back to 90%, with a revised median timeline of 5 billion years rather than 2 papers, the same data source, substantially different answers. The fate of our galaxy is, at this moment, genuinely uncertain. Andromeda is the most studied external galaxy in the sky. We have mapped its stars, measured its mass, tracked its rotation, identified its satellite galaxies, and found evidence of ancient collisions it has already survived. We know it is moving toward us. We have known this for over a century. What we do not know, with any certainty, is whether it will actually hit us. And the difference between will collide and a might collide comes down to a measurement, a single number. The precise sideways velocity of Andromeda relative to the Milky Way, measured in kilometers per second, from a distance of 5 million light-years. That number is currently known to within about 30 to 40 kilometers per second. And a change of that size in that number is enough to swing the outcome from a near certain merger to a near certain miss. This video is about the Andromeda Milky Way system and what is actually known, and genuinely unknown, about its future. It is about the physics of what happens when two spiral galaxies collide. Something we can watch happening to other galaxies right now, and can simulate with extraordinary precision. It is about the specific measurement problem that has made the fate of our own galaxy uncertain. Since Gaia's data introduced new precision and, simultaneously, new complications. It is about the June 2025 Nature Astronomy paper that put the merger probability at 50%, and the March 2026 counter paper that put it back at 90%, and what the disagreement between them actually tells us about the limits of what we can know from this distance. And it is about the broader picture of what a galaxy collision is and is not, because almost everything most people assume about what Andromeda hits the Milky Way would look like, for the stars, for the planets, for anything inside either galaxy, is wrong in ways that are surprising. By the end of this video, you will understand the genuine science of what a galactic collision means physically, why the fate of the local group is currently less certain than most coverage suggests, what the Sawala and Wu papers from 2025 and 2026 actually found, and where they disagree, and what the night sky would actually look like from Earth's solar system, assuming it survives, over the billions of years that a full merger takes to complete. If Andromeda is moving toward us at 110 kilometers per second, why do we not know whether it will actually collide with us? What is the specific measurement that remains uncertain? And why is measuring the sideways motion of a galaxy 5 million light-years away so difficult? What does a galaxy collision actually involve for the individual stars within those galaxies? And why does a collision not mean what most people assume? What is the Large Magellanic Cloud, and why does its orbit matter so much for whether the Andromeda merger happens at all? And if the merger does occur, on a timeline of 6 to 10 billion years, what would a human observer, if one existed, actually see in the sky over that period? This is not a video about a catastrophe heading toward Earth. Nothing about the Andromeda Milky Way interaction, if it occurs, poses any meaningful danger to our solar system, to Earth, or to any life that might exist here. The distances between individual stars are so vast that even in a full galaxy merger, the probability of any two stars colliding is essentially the Sun and Earth would almost certainly survive, displaced into a new orbit within whatever merged galaxy eventually forms, but intact. This is also not a video that treats the collision as certain, and its consequences as predictable. The most current science, as of mid-2026, leaves the merger probability genuinely uncertain. Somewhere between 50 and 90% depending on which Gaia measurement you trust, and the timeline uncertain, to within several billion years. The honest story is more interesting than the settled version most coverage tells. It is a story about what we can and cannot measure from where we are, about what galaxy collisions actually are and how we know, and about an event that, if it occurs, will unfold on timescales that make any human concept of event almost meaningless. Before we go further, if you like science that tells you both what we know and what remains genuinely uncertain, Rather than smoothing the uncertainty into a single confident headline, consider subscribing to Galaxy Pulse. Now, back to Andromeda, and the number that determines whether our galaxy has a collision in its future, or a narrow escape. To understand why we know so much about Andromeda, and still cannot be certain what it will do, we need to start with the basic physics of how two galaxies interact. Why measuring the key quantities from inside one of them is so difficult, and what the past few years of increasingly precise data have actually told us about the trajectory of the largest object in our cosmic neighborhood. The Milky Way and Andromeda are the two largest members of the local group, a collection of roughly 80 galaxies, most of them small dwarf galaxies, bound together by their mutual gravity in a volume of space roughly 10 million light-years across. Mass T of that volume is empty intergalactic space. The population is dominated by the two large spirals, our own Milky Way and Andromeda, with a third significant spiral, the Triangulum Galaxy at roughly 2.7 million light-years, and a retinue of smaller satellites around each of the major players. What makes the local group unusual, compared to typical galaxy environments across the universe, is not that it contains large galaxies, spirals of this kind are common, but that it contains two of them in close proximity, both massive enough to dominate the gravitational dynamics of their immediate environment, and close enough to each other that their interaction is not just a distant future prospect, but a present physical reality. The gravitational influence of Andromeda on the Milky Way, and vice versa, is already non-negligible. The outermost regions of both galaxies' dark matter halos already overlap. The orbits of dwarf galaxies in the local group are being shaped by the combined gravitational fields of both large spirals, not just one. The system we call the local group is, in a meaningful physical sense, already in the early stages of interaction. The local group itself is gravitationally bound. Its members are not drifting apart as the universe expands. They are orbiting each other, slowly, on timescales of billions of years. The large galaxies in the local group have histories of interaction. Andromeda shows evidence of having collided and merged with at least one other substantial galaxy in its past. A merger that left structural signatures still visible in the peculiar density of its inner region, and the presence of its unusual compact companion, galaxy M32. The Milky Way itself has absorbed several smaller satellite galaxies over its lifetime. The stellar halo around our galaxy contains populations of stars with chemical compositions and orbital properties that trace their origin to these ancient T incorporations. Galaxy mergers are not rare events in the universe. They are a normal part of how galaxies grow and evolve. The recognition that Andromeda was moving toward us dates back more than a century. The blue shift of its spectral lines, the compression of wavelengths indicating motion toward the observer rather than away, was measured in 1912 by Vesto Slipher at Lowell L Observatory in Flagstaff, Arizona. Slipher found Andromeda approaching at roughly 300 kilometers per second relative to the solar system. That large number comes from the fact that the Sun is itself orbiting the Milky Way's center at about 225 kilometers per second, in a direction that partly opposes Andromeda's motion relative to the galaxy as a whole. Once the Sun's orbital motion is accounted for, the galaxy-to-galaxy approach speed settles to approximately 110 kilometers per second, and it is this corrected number, the speed at which the Milky Way center and Andromeda's center are approaching each other, that has been known with good precision for decades. What has been much harder to measure is the transverse velocity, the component of Andromeda's motion sideways across the sky, neither toward nor away from us, but at an angle to our line of sight. This distinction matters enormously for the collision question. Imagine you are standing in a road and you see a car approaching from a distance. You can hear the pitch of its engine, and estimate from the Doppler effect how quickly it is coming toward you. But that tells you nothing about whether the car is aimed directly at you or slightly to one side. Even a car moving quickly toward you will miss if it is aimed far enough off-center. The approach speed, the radial velocity, tells you the car is coming. The transverse velocity determines whether you need to get out of the way. For Andromeda, the transverse velocity is the critical number. If Andromeda is moving almost purely along the line of sight, with very little sideways motion, it is aimed roughly at us, and a collision becomes more likely. If it has significant transverse motion, it might swing past the Milky Way rather than through it. Measuring this transverse velocity from Earth requires detecting an angular motion, a tiny shift in Andromeda's position on the sky over time, caused by its sideways movement across our line of sight. At 2.5 million light-years, this angular motion is extraordinarily small, even at 80 kilometers per second of true transverse motion. The apparent shift in position over 10 years is tinier than the angular width of a human hair seen from several kilometers away. This is not a matter of needing a bigger telescope or a longer exposure time. It is a measurement operating at the absolute frontier of what precision astrometry can achieve. This is the measurement challenge at the heart of the Andromeda story. Under the expectations set by older measurements, the Andromeda collision was a settled story. Hubble Space Telescope measurements, published in 2012 by Roland van der Merwe and colleagues, tracked the positions of stars in Andromeda over a 5 to 7 year baseline. Their data suggested Andromeda's transverse velocity was small, probably less than 35 kilometers per second, and statistically consistent with zero. If the sideways motion is near zero, the trajectory is nearly head-on, and a collision becomes almost inevitable. The simulations of the time gave a collision probability above 95%, with an expected first close passage in around 3.9 to 4 billion years. This was reasonable consensus based on the best available data. It generated a detailed, well-publicized picture of what the merger would look like, released by NASA in 2012, which showed simulated night sky views at different stages of the approach and mi-argeur. It set the 4.5 billion years figure that has been repeated in hundreds of articles and documentaries since, and it was, for its time, a genuine scientific achievement, tracking the apparent motion of stars in a galaxy 2.5 million light-years away to constrain a velocity uncertain at the level of tens of kilometers per second. It is worth pausing to appreciate how remarkable even that 2012 measurement was. Andromeda sits at 2.5 million light-years from Earth. Measuring the sideways motion of a galaxy at that distance is equivalent to trying to detect the sideways drift of an object placed roughly 25 billion times farther away than the Moon, over a baseline of just a few years. The fact that the Hubble measurement could constrain the transverse velocity to below about 35 kilometers per second at all, ruling out very large sideways motion, and establishing that Andromeda's trajectory was at least broadly aimed in our direction, represented years of careful observation and analysis. The uncertainty that remained, the difference between a very small sideways motion and, essentially zero sideways motion, was not a failure of technique. It was the honest limit of what was achievable. What changed when the Gaia satellite began releasing its own far more precise measurements of stellar positions and motions, was the degree of confidence in that transverse velocity estimate. Gaia can measure stellar positions to a precision of microarcs cons, roughly 100 times better than what Hubble's tracking of Andromeda's stars was able to achieve for this specific purpose. When Gaia data was applied to stars in Andromeda, it produced new transverse velocity estimates that differed from the Hubble measurements and came with their own complications. Those complications, specifically the question of which stars in Andromeda to use for the measurement, and how to correct for systematic errors in Gaia's astrometry at the angular scale of Andromeda's extent on the sky, turned a settled question into an active and unresolved debate between research teams using essentially the same raw data. The story of how the Andromeda merger went from near certain to genuinely uncertain runs through 3 key studies in the space of about a year. The first is the Sawala et al. Paper, published in Nature Astronomy in June 2025, led by Till Sawala at the University of Helsinki, with collaborators from Durham and Toulouse. The team used Gaia data alongside Hubble measurements and combined them with the most up-to-date mass estimates for all the major local group galaxies. Their key methodological choice was to include all 4 of the most massive local group members in their simulations: Andromeda, the Milky Way, the Triangulum Galaxy M33, and the Large Magellanic Cloud, rather than treating the Andromeda Milky Way system as a 2-body problem and handling the satellites as minor perturbations. This matters because the Large Magellanic Cloud has a mass of somewhere between 100 billion and 200 billion solar masses, enough to have a significant gravitational influence on the Milky Way's effective trajectory. The LMC was accreted by the Milky Way relatively recently in cosmic terms, probably within the past 1.5 billion years, and its orbit runs in a direction that is not aligned with the plane in which the Milky Way and Andromeda are approaching each other. This misalignment induces a sideways displacement in the Milky Way's center, a reflex motion, that changes the effective trajectory of the Milky Way relative to Andromeda, in ways that were not fully captured in older 2-body simulations. Adding the LMC as a 4th body to the simulation is not a minor technical refinement. It changes the geometry of the problem in ways that matter. When Sawala's team ran 100,000 simulations, sampling the full range of uncertainties in the current measurements, they found that roughly half of the simulations resulted in a merger within 10 billion years, and roughly half did not. The merger probability dropped to approximately 50%. The team was careful about what this meant. They were not claiming the merger would not happen. They were claiming that current data is insufficient to say definitively whether it will. This result received significant media attention and considerable scientific discussion. Some researchers accepted it as a reasonable reflection of genuine measurement uncertainty. Others were more skeptical, not of the simulations themselves, but of the specific Gaia proper motion values used for Andromeda. The objection was technical, but important. The Gaia proper motion values used in the Sawala paper may not have been fully corrected for a known systematic offset in Gaia's astrometric solution at large angular separations from the satellite's calibration sources. This led directly to the second key study, published as a preprint in March 2026 and formally in a peer-reviewed journal in April 2026, by Hao Wu and colleagues. Wu's team used the same semi-analytic framework as Sawala, but adopted different Gaia-based PR-upper motion measurements for both Andromeda and M33. Specifically, values that had been corrected for systematic offsets in Gaia's astrometry, a known issue in Gaia's data processing that affects measurements of objects far from the calibration reference, STARS. With these corrected measurements, and 10,000 simulations using the same overall approach, the merger probability in Wu's fiducial model rises to 90%, with a median merger time of 6.5 billion years. The classical picture is broadly restored, with an important caveat. Wu's paper also includes a detailed sensitivity analysis, showing explicitly that the merger probability depends extremely strongly on exactly which proper motion value is adopted for Andromeda. Across the full 2 sigma uncerta NTY range in the Gaia measurements, the merger probability in their framework spans from about 65% at the low end to 100% at the high end. Current measurement precision, with uncertainties of about 8 microarcseconds per year per component of proper motion, is insufficient to draw a firm conclusion about which end of that range reflects reality. In other words, both papers are telling essentially the same story from different angles. The Sawala paper says, the measurement uncertainty is large enough that we cannot exclude a miss. The Wu paper says, with slightly better measurements, the probability looks higher, but the measurements are not yet precise enough to be definitive. Both agree on the underlying problem. The fate of the local group depends sensitively on a measurement that is not yet precise enough to settle it. Let's make a few concepts concrete here, because they are essential for understanding why this measurement is so difficult and what the collision would actually mean in physical terms. Proper motion is the apparent angular shift in an object's position on the sky caused by its true motion through space in a direction not exactly aligned with our line of sight. For nearby stars, Gaia measures proper motions that correspond to real velocities of tens of kilometers per second, and the precision is extraordinary. Positional shifts of a few microarcseconds per year are routine. For Andromeda, the challenge is different in kind, not just degree. Andromeda is not a point source. It is a galaxy containing billions of stars spread across a region of sky several degrees in diameter, each of those stars orbiting Andromeda's center, rotating with it, and moving individually within it. Separating all of these internal motions from the one true bulk motion of the entire galaxy requires both an enormous sample of stars and very careful correction for systematic errors in the measurements. Any unaccounted systematic bias in the measured positions of Andromeda's stars, even one of a few microarcseconds, translates into a false apparent bulk motion that can mislead the inference about the galaxy's actual velocity. The Large Magellanic Cloud is one of the Milky Way's satellite galaxies, visible as a bright cloud-like patch in the southern sky from the southern hemisphere. It is a smaller galaxy, irregular in shape, rich in gas and young stars, with a mass of roughly 10 to 15% of the Milky Way's total mass, including dark matter. This makes it substantial. Not a negligible companion, but a meaningful fraction of the Milky Way system's total gravitational budget. As the LMC follows its orbit and spirals closer to the Milky Way, the Milky Way's own center responds, displaced slightly from where it would otherwise be by the gravitational pull of this orbiting mass. This displacement creates a reflex motion of the Milky Way's center that, when not accounted for, introduces an error into the measurement of Andromeda's velocity relative to the Milky Way. Because we measure everything from our position inside the Milky Way, and because the Milky Way's center is itself wobbling due to the LMC, correcting for this wobble is not optional. It is essential for getting the right answer. This is perhaps the most widely misunderstood aspect of the Andromeda merger, and the answer is both reassuring and strange. The distances between stars, even within a dense galactic disk, are so enormous relative to the sizes of the stars themselves that when two galaxies pass through each other, individual stars almost never come anywhere near each other. The Milky Way contains roughly 200 to 400 billion stars spread across a disk about 100,000 light-years in diameter. The average distance between stars in our neighborhood is about 4 to 5 light-years, and a light-year is nearly 10 trillion kilometers. 2. Galaxies merging is not like two clouds of dust colliding, where the individual particles crash into each other. It is more like two enormous swarms of fireflies moving through each other in the dark, with each firefly so far from all the others that the two swarms pass through each other, almost without any individual firefly noticing the presence of the other swarm. What does change dramatically is gravity. Stars in both galaxies experience completely new gravitational environments as the two massive systems interact, their familiar orbits disrupted, some redirected into highly eccentric paths, some flung outward into wide halos, a small fraction ejected entirely from both galaxies. Gas clouds in both galaxies collide directly. Gas, unlike stars, is spread continuously rather than concentrated in point-like objects, so gas truly does collide. And the shock of those collisions compresses gas into dense regions that ignite as new star-forming sites. The merger triggers starbursts. The spiral structures of both galaxies are unraveled by tidal forces. The final product, after the multiple passes and eventual coalescence of the two cores, is typically a large elliptical galaxy with no spiral structure. A smooth, slowly rotating, gas-poor system. Its earlier character replaced by the mixed inheritance of both progenitors. We can watch galaxy mergers happening right now. Not our own, but other pairs at various stages of the process, scattered across the observable universe. Some of the most striking objects in any deep sky catalog are interacting galaxy pairs. The antennae galaxies, NGC 438 and 439, about 45 million light-years away in the constellation Corvus, show two spiral galaxies whose outer arms have been drawn into enormous tidal tails extending far from each galaxy's core. The mice galaxies, named for the long tails they trail, are another pair caught in a similar interaction. The Whirlpool galaxy, M51, shows the distorting influence of a companion galaxy pulling on one of its spiral arms in real time. These are not rare exceptions. Interacting and merging galaxy pairs appear throughout deep imaging surveys at all distances, providing a vast library of examples at different merger stages that can be compared against simulations to calibrate our models. From these observed examples, and from detailed computer simulations, astronomers have assembled a fairly precise picture of how a merger between two large spiral galaxies like the Milky Way and Andromeda would unfold over billions of years. The following draws on simulations calibrated against observed merging galaxy pairs, recognizing, as discussed, that the exact timeline and geometry remain uncertain. The first stage is the approach. Gravity gradually accelerates both galaxies toward each other as the distance shrinks. Even now, the halos of dark matter surrounding both galaxies already overlap at their outer edges. The galaxies begin to distort even before they reach each other. Tidal forces, the differential gravitational pull felt by the near side versus the far side of each galaxy, begin to stretch the disk of each galaxy toward the approaching partner. This distortion is subtle at first, below the threshold of anything a human observer would notice on the timescale of a single lifetime. By roughly 3.75 billion years from now, according to simulations based on a merger trajectory, Andromeda would be visible in Earth's sky as a dramatically larger structure than the faint smudge it appears today, spanning several degrees across, its spiral arms beginning to resolve individual structure to the naked eye. The night sky at that point would be transformed in a way no human alive today can fully picture. A second spiral galaxy, as bright and large as a significant fraction of the Milky Way itself, dominating one region of the sky, slowly growing across the years, unmistakably there. The first close passage, if it occurs, is the event that most dramatically reshapes both galaxies. The cores of the two galaxies pass near each other, not necessarily touching, but close enough for tidal forces to become extreme. Spiral arms shred. Stars f-rum. Both galaxies are flung into wide orbits, or ejected entirely. Gas clouds in both galaxies collide, and the shock of those collisions compresses gas into new star-forming regions, triggering a burst of stellar formation, unlike anything in the current quiet state of either galaxy. The stellar birth rate in both galaxies, during and after the first passage, could increase by factors of 10 or more compared to today. The first close passage, if it occurs, is the event that most dramatically reshapes both galaxies. The cores of the two galaxies pass near each other, not necessarily touching, but close enough for tidal forces to become extreme. Spiral arms shred. Stars f-rum. Both galaxies are flung into wide orbits, or ejected entirely. Gas clouds in both galaxies collide, and the shock of those collisions compresses gas into new star-forming regions, triggering a burst of stellar formation, unlike anything in the current, quiet state of either galaxy. The stellar birth rate in both galaxies, during and after the first passage, could increase by factors of 10 or more compared to today. It is worth pausing on what this starburst phase would mean for an observer living through it, not because any human will, but because it makes the physical reality more concrete. Both galaxies currently form stars at modest rates. The Milky Way produces roughly 3 to 5 new stars per year. Andromeda produces closer to 1. During the peak starburst triggered by the first close passage, the rate of star formation across the combined system could jump by an order of magnitude or more. Regions of compressed gas would ignite as clusters of hundreds or thousands of new massive stars simultaneously. These massive stars live short, brilliant lives, and their deaths as supernova would scatter chemical elements, oxygen, carbon, iron, silicon, through the surrounding gas at high rates, rapidly enriching the stellar material. The merged galaxy that eventually forms would have a stellar population history reflecting this burst. A large population of stars formed in the old, quiet Milky Way and Andromeda. Then, a wave of stars formed in the starburst triggered by the merger. Then a declining and eventually quiet star formation rate as the gas supply is exhausted. The two galaxies then swing apart, decelerated by the gravitational drag of the interaction. They slow, stop, and begin to fall back toward each other. Simulations suggest the first pass would be followed by a second close approach, and then perhaps a third, each time the galaxies spiraling closer and more disrupted, over a period of perhaps 1 to 2 billion years. Eventually, the two cores approach each other for the last time and merge. What remains after all of this is no longer two spiral galaxies. It is a single, large elliptical galaxy, its spiral structure destroyed by the billions of years of tidal disruption, its gas supply largely exhausted in the star formation bursts triggered by the merger. This object is sometimes called Milkomda in popular W writing, a placeholder name for a structure that will not exist for billions of years. One detail that almost never appears in popular coverage deserves a moment here. From the perspective of a hypothetical observer somewhere in the Milky Way during the merger, the experience would not be of stars hurtling past at tremendous speeds. The star S of Andromeda's disk would be visible as a second diffuse band of light spread across the sky, brighter than the current Milky Way band, perhaps far brighter during the peak of the starburst. But the individual stars would be no more individually distinguishable than the stars of our own galaxy are to the naked eye now. No single Andromeda star would appear as a discrete bright point, unless it happened to be among the intrinsically most luminous in the entire galaxy. The collision would look, from inside, like a transformation of the sky over billions of years, not a sudden catastrophe, but a slow, profound reshaping of everything overhead. This is almost certain. The question most people actually want answered, and the honest answer is less dramatic than many expect, and strange in different ways. The Sun is currently located about 26,000 light-years from the Milky Way's center, in what is called the Orion Arm, a minor spiral arm of the galaxy. During the merger, the Sun's position within the resulting merged galaxy will change, almost certainly. Change here means on timescales of hundreds of millions to billions of years, and does not mean anything catastrophic or sudden on any human timescale imaginable. The probability of the Sun physically colliding with another star during the entire merger process is essentially zero. As noted earlier, stars are separated by vast distances, even in a dense galactic disk. During the close passages and eventual merger of the two galaxies, the local density of stars around the Sun would increase somewhat as stars from both systems are mixed into similar orbits. But the probability of any star coming within even a light year of the Sun over the entire merger process is small, and the probability of an actual physical collision between stars remains negligible throughout. What might change, on very long timescales, is the Sun's orbital position within the merged galaxy. Simulations from the 2012 Van der Merel study, which remain the most detailed available for the solar system's fate. Updated simulations for the 2025-2026 T-trajectory parameters have not yet been published. Suggest that roughly 5% of stars from both original galaxies are ejected entirely during the merger, flung into wide orbits well outside the main body of the merged galaxy. The Sun has a small probability, perhaps a few percent, of ending up in this ejected population. More likely, it ends up somewhere within the merged elliptical galaxy, at a distance from its center that might be greater or smaller than its current distance from the Milky Way's center, with an orbital shape that is more elliptical and less circular than its current nearly circular path. Earth, assuming it still exists by this point, which is itself uncertain. Given that the Sun will expand into a red giant and very likely consume the inner planets, including Earth, in roughly 5 billion years, would experience none of the merger-related changes directly. The changes occur on timescales far too long for any single orbit, or any single lifetime, or any recognizable civilization to detect. Any honest account of the Andromeda merger has to address dark matter, because the outcome depends as much on the dark matter content and distribution of both galaxies as it does on anything else. Dark matter, the invisible component that accounts for roughly 85% of the mass of a typical galaxy, does not interact with light and cannot be directly observed. Its presence is inferred from its gravitational effects on the rotation curves of galaxies, on the bending of light around galaxy clusters, on the large-scale structure of the universe. Both the Milky Way and Andromeda are surrounded by enormous halos of dark matter that extend far beyond their visible stellar disks, to radii of several 100,000 light-years. The sea halos are not dense compared to the visible galaxy at its center, but they are enormous in extent, and the total mass they contain rivals or exceeds the visible stellar mass. Measuring the mass of the Milky Way's dark matter halo is a particular challenge because we are inside it. Methods that work well for external galaxies, measuring how fast the outer parts of the galaxy rotate, for instance, and inferring the enclosed mass s from the orbital speed, work less cleanly when the measurement is made from within the system. Instead, astronomers use a range of indirect methods, tracking the orbits of distant satellite galaxies and star streams at large radii, where the enclosed ma-ss determines the orbital velocity, measuring the escape velocity of the fastest moving stars observed in the halo, which sets a lower limit on the total gravitational potential, and using the timing argument, which infers the total mass of the local group from the fact that the Milky Way and Andromeda have already turned around from the Hubble flow and are now approaching each other. Each of these methods comes with its own systematic uncertainties, and they do not all agree with each other. The result is that the Milky Way's total mass, dark matter halo included, is currently uncertain. Within a factor of roughly 2, with estimates spanning from around 500 billion solar masses at the low end to well over 1 trillion solar masses at the high GH end. This is not a minor uncertainty. It is the difference between the Milky Way being significantly less massive than Andromeda, roughly equally matched, or more massive. And, since the gravitational dynamics of the merger depend on the mass ratio of THE2 participants, this uncertainty feeds directly into the range of predicted merger timescales and outcomes. When two galaxies approach each other, their dark matter halos begin to interact long before the visible stellar components do. The halos interpenetrate and generate gravitational friction, called dynamical friction, that removes energy from the relative motion of the two galaxy cores and causes them to sink toward each other faster than they would in the absence of dark matter. Dark matter halos are the primary driver of merger timescales. A galaxy without a dark matter halo would be far less likely to merge with a neighbor, even in a close passage. Because, without the halo's gravitational drag, there would be nothing to slow the galaxy enough to prevent it from just swinging past. The mass of the Milky Way's dark matter halo is genuinely uncertain, with estimates ranging from around 500 billion to over 1 trillion solar masses, depending on the measurement method used. This mass uncertainty is one of the 3 main sources of uncertainty in predicting the merger outcome, alongside the transverse velocity uncertainty and the influence of the Large Magellanic Cloud. The fact that we do not know the mass of our own galaxy to within a factor of roughly 2 is not a failure of modern astronomy. It is an honest reflection of how difficult it is to measure something that does not emit, absorb, or reflect any light. There are 3 distinct ways to frame the Andromeda Milky Way story, and they each lead to a somewhat different understanding of what we are actually learning from the current scientific debate. The first framing treats this primarily as a measurement story. In this view, the interesting thing happening right now is not anything about the future fate of these 2 galaxies, which will not be resolved on any human timescale, regardless of what the emulations say. The interesting thing is the extraordinary precision that Gaia has brought to measuring the motion of an entire galaxy, 5 million light-years away. A precision so high that it can distinguish between scenarios that differ by 20 to 30 kilometers per second in a velocity measured from a distance of tens of billions of kilometers. The disagreement between Sawala and Wu is, in this view, exactly the kind of productive scientific dispute that frontier precision measurements generate, and its resolution, whenever it comes, will be a genuine advance in our ability to measure the dynamics of the local group. There is also a broader point in this framing about how scientific precision interacts with scientific certainty. It might seem intuitive that more precise measurements should always produce more certain conclusions. But this is not always true. A less precise measurement, if it is consistent with only one hypothesis, can produce confident conclusions despite its coarseness. A more precise measurement, if it reveals that the answer is sensitive to parameters that were previously assumed to be negligible, Ka-n, actually reveal new uncertainty, even as it improves raw precision. This is exactly what happened with Gaia. The satellite's unprecedented precision in measuring stellar positions revealed that the outcome depends sensitively on systematic corrections to those positions that were previously too small to matter. And, in revealing this dependence, it replaced the confident 2012 picture with a genuinely uncertain one. The second framing treats this as a story about the completeness of our models. Before the LMC's influence was properly modeled, the Andromeda merger looked near certain. After it was included, the probability dropped to 50%. After correcting for systematic Gaia errors, it rose to 90%. Each of these steps required adding something to the model that the previous version had left out or treated inadequately. The lesson is about how much the outcome depends on getting the inputs right, and how easy it is to have false confidence in a prediction when a model is internally consistent, but missing a key physical ingredient. The third framing treats this as a story about our place in a dynamic, evolving universe. The Milky Way is not a permanent structure. It has a past, marked by ancient mergers that left chemical signatures in its stellar populations. It has a future that involves continued interaction with its satellite galaxies, potential interaction with Andromeda, and eventual structural transformation into something unrecognizable to any observer familiar with the current night sky. The uncertainty about whether and when the merger will happen does not change the larger picture. It is a normal part of how the universe works, as seen from inside one of the participants. All three framings are simultaneously valid. The measurement is genuinely important. The modeling lessons are genuinely instructive. The larger context, a galaxy with a past full of mergers, embedded in a dynamic local group, on a trajectory we are still working out, is the accurate description of where we are. What none of these framings support is the simple version. Either the confident collision in 4-5 billion years, here is exactly what it will look like, narrative, or the sensationalized scientists say Andromeda won't hit us after all. Counter-narrative. The science in mid-2026 sits between those two poles, more interesting and more honest than either. The detailed story of what current data says, what the two recent papers actually found, and where the open frontiers of the measurement lie, continues in part 2. Let's come back to where we started. Andromeda is moving toward us at approximately 110 kilometers per second. The galaxy-to-galaxy approach speed, after accounting for the Sun's own motion around the Milky Way's center. That fundamental fact has been known in one form or another, since Vesto Slipher measured the blueshift of Andromeda's light in 1912. Though his raw figure of around 300 kilometers per second was a heliocentric number that needed correction for the Sun's own orbital velocity. We have known something big is coming for over a century. What we do not know, with the precision needed to settle the question, is exactly how much sideways motion accompanies that approach. That one number, the transverse velocity, currently measured to within about 30 to 40 kilometers per second of uncertainty, is the difference between a near-certain merger and a coin flip. It is the difference between the June 2025 Sawala paper and the March 2026 Wu paper. And it is the number that future Gaia data releases and dedicated proper motion campaigns are most likely to refine. Though Whether any single new dataset will refine it enough to settle the debate depends on whether the systematic errors that Wu's team corrected for are properly handled in the new measurements. What we know for certain is this: Andromeda is close enough and massive enough that the gravitational interaction between these two galaxies is already underway, has been underway for billions of years, and will continue regardless of whether the eventual outcome is a merger or a wide pass. The local group is not static. It is dynamic, evolving, reshaping on timescales that dwarf human civilization, but are well within the scope of what cosmological models can describe. It is worth being clear about what that ongoing interaction means in practice. Gravitational influence does not require physical contact. At a distance of 2.5 million light-years, Andromeda's dark matter halo already overlaps, at its outskirts, with the Milky Ways. The two galaxies have been exerting measurable gravitational effects on each other for longer than the Earth has existed. What is still uncertain is not whether these two galaxies affect each other, they do, but whether their current trajectories will eventually bring their centers into the same region of space, triggering the kind of dramatic structural disruption and stellar redistribution that we classify as a merger, or whether one will pass close enough to leave significant tidal scars before continuing on a different trajectory. There is something worth pausing on in the phrase, trajectories will eventually bring their centers into the same region of space. This is a statement about what happens over multiple billions of years, and the path between here and there is not a simple straight line. Most galaxy mergers, including the one modeled for the Milky Way and Andromeda, if the merger scenario plays out, do not happen in a single pass. The first close approach strips material from the outer regions of both galaxies, creating long tidal tails of stars flung outward into intergalactic space. The two cores then recede from each other somewhat before gravity pulls them back for a second approach, which is typically closer and more disruptive, followed by additional passes that progressively drain orbital energy from the system until the two cores finally settle into one combined structure. This sequence, first pass, rebound, second pass, eventual coalescence, can take hundreds of millions to over 1 billion years from start to finish. At no point during this sequence is any individual star likely to physically collide with another, because the distances between stars are so enormous relative to the sizes of the stars themselves. What changes during a merger is the large-scale structure. The spiral arms are destroyed, the gas is compressed and driven to form new stars in enormous starbursts, and the final product, after all the dynamical mixing, is typically a large, smoothly distributed elliptical galaxy, its earlier spiral structure G1, entirely. The coverage of the Andromeda collision exists in two distinct periods, and both periods have had characteristic blind spots. Before June 2025, virtually every popular article on the topic treated the merger as settled science, repeating the 4.5 billion year figure as established fact, often citing the 2012 NASA visualization without noting the significant measurement uncertain whys underlying it. The 2012 van der Merel et al. Study was a genuine scientific achievement, providing the first proper motion measurement of Andromeda's transverse velocity from Hubble data. But the way that result was communicated to the public tended to flatten its uncertainty bars into a confident prediction. The phrase, "on a collision course," became standard, without the qualifier that collision course was a median outcome from a probability distribution, not a geometric certainty. After the Sawala paper in June 2025, a wave of Andromeda may not hit us after all coverage appeared, which, while more accurate in some respects, tended to overstate what Sawala had actually found. The paper did not say the merger would not happen. It said the probability was roughly 50%, which is very different from claiming a near miss. A 50-50 outcome is one of the most genuinely uncertain predictions in science. It corresponds to maximum uncertainty, not to the no collision, framing at some headlines adopted. At that level of probability, saying, may not hit us, is exactly as accurate and exactly as misleading as saying, may hit us. Both framings are technically true, and neither conveys the actual state of knowledge. And the Wu counterpaper from March 2026, which largely restored the classical picture using more carefully corrected Gaia measurements, received almost no popular coverage at all, despite being published in a peer-reviewed journal in April 2026, and direct lie addressing the most scientifically contested aspect of the Sawala result. Here are the specific things that most coverage has consistently missed. The transverse velocity problem. Almost no popular article about the Andromeda merger explains what a transverse velocity is, why it is so hard to measure at extragalactic distances, and why the outcome depends on it so sensitively. Without this context, our readers have no way to understand why two research teams using data from the same Gaia satellite can reach such different conclusions, or why the difference between a 50% and a 90% merger probability is rooted in something as technically specific as whether a particular systematic offset in the Gaia astrometric solution has been corrected for. The measurement challenge is the story it almost never gets told, the role of the Large Magellanic Cloud. The LMC has been the subject of significant recent research in its own right, as astronomers have recognized that its ongoing infall into the Milky Way's gravitational well has had measurable effects on the shape and dynamics of the Milky Way's dark matter halo. The LMC is, in a gravitational sense, already shaking the floor beneath us, creating a reflex motion of the Milky Way's center that needs to be carefully accounted for when calculating Andromeda's relative trajectory. Its role in the Andromeda merger prediction is rarely mentioned in popular coverage, even though it is one of the three main sources of uncertainty in the calculation, alongside the measurement of Andromeda's proper motion itself and the uncertain n masses of both galaxies. The dark matter mass uncertainty. Both the Milky Way and Andromeda have uncertain total masses, driven largely by uncertain dark matter halo masses extending well beyond their visible stellar disks. This uncertainty is a significant input into merger times calculations and contributes to the range of outcomes in simulations. The fact that we do not know the total mass of our own galaxy to within a factor of roughly 2 is itself a striking piece of information that rarely makes it into popular accounts, and it underlies why even the most precise trajectory measurement cannot fully constrain the merger outcome on its own. The Wu et al. Counter result from 2026. A peer-reviewed paper, formally published in April 2026, finding that the merger probability is 90% with updated and systematically corrected Gaia measurements, directly addresses and partially reverses the conclusio N that drove most of the popular coverage of the Sawala paper. This paper has been almost completely absent from popular science coverage. What the actual night sky would look like. Popular accounts of the Andromeda merger focus almost entirely on simulations of what the galaxies look like from outside. Dramatic images of two spirals interacting from a third-party vantage point somewhere in intergalactic space. The question of what an observer on Earth, or on a planet somewhere in the Milky Way, would actually see across billions of years of approach and eventual merger, how the night sky changes, how long the process takes, what a single human lifetime placed anywhere in that sequence would witness, is more concrete, more humanly scaled, and almost never addressed in detail. The most significant recent development is the Wu et al. Paper from March 2026, and what it implies about the current state of the measurement. Wu's team performed a sensitivity analysis that is worth understanding in some detail, because it reveals exactly where the uncertainty lies and what kind of data would be needed to resolve it. At the heart of the disagreement between Sawala and Wu is a question about which value of Andromeda's proper motion to trust, and specifically, how to handle a systematic offset in the Gaia astrometric solution that affects measurements of objects in M31's vicinity. The Gaia satellite, though extraordinarily precise, has known systematic biases in its measurements of stellar positions and motions that vary across the sky. And correcting for these systematics is a technically demanding process that can mean fully affect the inferred proper motion of a distant galaxy's stars. Sawala's team used a Gaia-based proper motion without applying a systematic correction that Wu's team later argued is necessary. Wu's team applied that correction, which yielded a slig HTLY different proper motion value for Andromeda, one that translates into a higher merger probability. To understand why a small difference in a proper motion value can produce such a large swing in merger probability, from 50% to 90%, it helps to think about the geometry. The radial velocity of Andromeda, its motion directly along our line of sight, is k known precisely from spectroscopy, and is approximately 110 kilometers per second in the galaxy-to-galaxy rest frame. This component of the motion is not in dispute. What is uncertain is the transverse velocity, how much Andromeda is moving sideways relative to our line of sight. At Andromeda's distance, a transverse velocity of 50 kilometers per second corresponds to a tiny angular drift in the sky of only a few tens of microarcseconds per year. The current Gaia precision is around 8 microarcseconds per year per component, and the systematic correction at issue is of comparable size to this uncertainty. A shift of even 20 kilometers per second in the inferred transverse velocity can, depending on the geometry, change the character of the encounter. From a trajectory that would just barely lead to gravitational capture and eventual merger, to one that would result in a wider pass with the galaxies escaping each other's gravitational well. The merger probability in their simulations depends very strongly on two things. First, the balance between the radial and transverse components of Andromeda's motion, the ratio of how much of its velocity is aimed directly at us versus how much is aimed sideways. Second, how this ratio interacts with the satellite-induced barycentric shifts, the wobbles in the Milky Way's effective center caused by the Large Magellanic Cloud's orbit. These two effects interact in a way that is geometrically sensitive. The proper motion of M31 sets not just the magnitude of the transverse velocity, but also the orientation of the Milky Way M31 orbital plane. And this orientation determines how the LMC-induced motions project onto that plane. Small changes in the adopted proper motion can flip the satellite effects from suppressing the merger probability to enhancing it, which is part of why Sawala and Wu reach such different answers from superficially similar calculations using data from the same satellite. Wu's paper explicitly states that current Gaia precision, about 8 microarcseconds per year per component of proper motion, is insufficient to draw a firm conclusion. Across the full 2 sigma uncertainty range of the proper motion values, the merger probability in their framework still spans from about 65% to 100%. To narrow this to the point of a decisive conclusion would require reducing the proper motion uncertainty by roughly a factor of 4. to below about 2 microarcseconds per year. His level of precision might eventually be achievable through continued Gaia operations, dedicated Hubble proper motion campaigns, or future missions like the proposed Theia astrometry satellite. Though none of these is guaranteed to reach the required level on any specific timescale. A note on Gaia's data releases. The satellite has been accumulating data for over a decade, and each successive data release incorporates a longer baseline of observations, reducing random measurement noise and improving the handling of some systematic EFFX. The scientific community has been anticipating further data releases that will continue to improve proper motion precision for objects throughout the sky, including Andromeda. Whether any forthcoming release will fully settle the merger question, DP-NDS, on whether the systematic biases at issue can be adequately characterized, which is itself an ongoing area of work within the Gaia team. Beyond the immediate measurement question, the Andromeda Milky Way system is the best nearby laboratory we have for studying large galaxy merger dynamics at high precision. And the recent papers have made this laboratory considerably more scientifically productive, not by resolving the question, but by sharpening it. The recognition that the LMC plays a significant role in the outcome has opened a new line of inquiry into how the LMC's infall has already affected the Milky Way, separate from any future Andromeda interaction. There is substantial current research into HO. The LMC's passage has disturbed the Milky Way's dark matter halo, created asymmetries in the halo's distribution, imparted a net reflex motion to the Milky Way's center that affects how we interpret measurements taken from within it, and may be partial Y responsible for features in the outer stellar disk that look like ripples or warps. Understanding the LMC Milky Way interaction in its own right has become directly relevant to understanding the broader question of how the local group will evolve. And the papers on both sides of the Andromeda merger debate have contributed to clarifying how the LMC's influence enters the calculation. It is worth unpacking what it means, precisely, for the LMC to affect the Milky Way's center of mass. The LMC has a mass of roughly 10% of the Milky Way's dark matter halo, which makes it a substantial fraction of the Milky Way system's total mass. Not a negligible satellite, but a genuinely significant body. As the LMC orbits and falls deeper into the Milky Way's gravitational potential, the Milky Way's center responds gravitationally, displaced slightly from where it would otherwise be. This displacement, sometimes called the reflex motion of the Milky Way's center, means that when we measure Andromeda's velocity relative to the Milky Way using measurements anchored to the Sun's position, we need to account for the fact that the Sun itself is orbiting a Milky Way center that is being shifted by the LMC. Not accounting for this correctly leads to a systematic error in the inferred Andromeda velocity, which in turn affects the merger probability calculation. This is one of the key physical insights that has emerged from the recent round of papers, and it is the kind of subtlety that does not appear in simplified treatments of the Andromeda collision problem. The precision, proper motion measurement of Andromeda is also a template for how astronomers will approach similar measurements in other galaxy groups. As astrometric missions accumulate longer baselines and better systematic error control, measuring the transverse velocities of the nearest galaxies in the local volume will become a standard technique for probing the dynamical state of galaxy groups more broadly. The Andromeda Milky Way system, with its rich history of increasingly precise measurements, PROV-IDs a uniquely well-characterized test case for methods that will eventually be applied elsewhere. And, on the timescale of the merger itself, The theoretical and simulation community continues to develop increasingly detailed models of what the merger would look like in specific observable quantities. The star formation history, triggered by gas-cloud collisions during the initial pass and subsequent approaches, the distribution of stellar orbits in the eventual elliptical remnant, the orbital evolution of the two central supermassive black holes as they sink toward each other over billions of years, the gravitational wave signal they would eventually emit, and the long-term chemical evolution of the merged galaxy's stellar populations. Each of these is a tractable scientific question, and the Andromeda Milky Way system provides the best available constraint (NTS) for calibrating those models, regardless of whether the answer to the immediate question of a merger or not is finally settled. Here is what this story is actually about, underneath the specific measurement dispute and the specific timeline uncertainty. We are living inside a galaxy that is moving, not just rotating, though it is rotating. Every star in the Milky Way is orbiting the galactic center, the Sun among them, completing one circuit every roughly 225 million years. Not just orbiting within the L-Ocal group, though it is doing that too, but moving on a long cosmic trajectory through a dynamic environment that has already shaped its history through past mergers and encounters, and will shape its future through the interactions that are currently underway. Most of us carry a mental picture of the Milky Way as a kind of fixed background, the stage on which the rest of the universe plays out. The stars visible in the night sky feel permanent. The galaxy itself feels like a permanent structure, something that was always here and will always be here in roughly this form. The Andromeda story is a corrective to that picture. The Milky Way as it currently exists is a temporary configuration. Its spiral structure will not last forever. Its current stellar population mix, its current size and shape, the arrangement of its Saddle-like galaxies, its particular relationship to Andromeda across 5 million light-years of intergalactic space. All of these are stages in a process that began long before the solar system formed and will continue long after the Sun burns out. The Milky Way itself bears the record of earlier mergers, though they are harder to read than in Andromeda. Within our galaxy's stellar halo, the roughly spherical cloud of old stars extending well beyond the disk, there are distinct populations of stars whose chemical composition and orbital properties suggest they were accreted from separate smaller galaxies billions of years ago, rather than forming in the Milky Way itself. One of these ancient merger events, which may have involved a galaxy of considerable mass on cosmic terms, appears to have contributed a significant fraction of the stars in the inner stellar halo and may have helped trigger the formation of the thick disk. The galaxy we inhabit has merged before. It simply did so early enough, and TE evidence has been mixed thoroughly enough into the overall structure that the merger scars require specialized spectroscopic surveys of individual stars' chemistry and orbits to read. Andromeda itself is not pristine. It carries the record of its own merger history in the structure of its halo, giant stellar streams, the remnants of smaller galaxies that were incorporated into Andromeda billions of years ago and are still being mixed into its outskirts. One of the most significant of these past events, which appears to have involved a galaxy with mass comparable to the Milky Way, may be responsible for the unusual density of stars in Andromeda's inner regions, and for the presence of a distinct compact companion, called M32. The Andromeda we see today is already a merger product, and it is heading, at some level of probability, toward another one. What the measurement debate between Sawala and Wu ultimately reveals is not uncertainty about whether our galaxy will be destroyed. Galaxies are not destroyed in mergers, they are transformed. Stars pass through each other's galaxies. Because the distance s between stars are so large relative to stellar sizes that direct stellar collisions during a galaxy merger are extraordinarily rare. What is destroyed, in the sense of being unrecognizable afterward, is the specific arrangement of structure, the spiral arms, the disk, the particular relationship between stars and gas and dark matter that we currently think of as the shape of our galaxy. What the measurement debate reveals is something subtler and more interesting. That even in the era of the most precise space-based astrometry ever achieved, the specific trajectory of the largest object in our cosmic neighborhood remains uncertain, to a degree that makes a meaningful difference to predictions about the future. That precision measurement, at these distances and on these timescales, is genuinely hard. That the universe does not give up its future plans easily, even to the best instruments we have built, and that looking up at that faint smudge in the constellation, Andromeda, knowing that something there is in motion relative to us, knowing that our best telescopes have now pinned down its speed and direction to the level of microarcseconds per year, and still not knowing quite where it will end up, is one of the more honest descriptions of where observational astronomy stands in mid-2026. We are watching, we are measuring, we are arguing productively about the measurements, and the galaxies keep moving, indifferent to our uncertainty, following their own trajectories through the dark. There is one more piece to this story that deserves its own telling. If the Milky Way and Andromeda do merge, the two supermassive black holes at their centers, currently separated by 5 million light-years, will eventually find themselves orbiting each other. This will not happen quickly. First, the galaxies as a whole must merge, a process taking hundreds of millions of years of repeated passes. Then, the two black holes, each carried by the stellar mass surrounding them, must sink toward the center of the merged galaxy through a process called dynamical friction, losing orbital energy to the surrounding stars over hundreds of millions of years more. Eventually, when their separation has shrunk to the point where direct gravitational wave emission can carry away the remaining orbital energy efficiently, they will spiral together over a still shorter but still enormous span of time. There is a subtlety here worth noting, because it connects to one of the most interesting open problems in astrophysics: dynamical friction, the process by which a massive object moving through a background of lighter objects loses momentum, because it gravitationally deflects those objects in a way that creates a slight net drag behind it, is efficient when there are many stars to deflect. But, as the two black holes spiral closer and closer together, they gradually eject stars from the region between them, depleting the very population of stars they need to keep losing orbital energy through dynamical friction. At some point, they may stall at a separation where dynamical friction is no longer efficient and direct gravitational wave emission is not yet strong enough to take over. This final parsec problem, the question of whether a pair of supermassive black holes can bridge the gap between a separation of roughly a parsec and the sub-parsec range where gravitational waves carry the rest of the orbit, has been an active area of theoretical research for decades, and the mechanisms that might resolve it, including interactions with gas, triaxial stellar distributions, and the presence of additional black holes, are still being worked out. For the Andromeda Milky Way system, the answer to this problem will determine whether the two black holes ultimately merge at all, or whether they orbit each other at close range, indefinitely. The gravitational wave signal from the final inspiral and merger of two supermassive black holes, each weighing millions to hundreds of millions of times the mass of the Sun, would be the most powerful low-frequency gravitational wave event in the local universe. The frequency of these waves is far below what ground-based detectors like LIGO can sense, because the orbital period of two supermassive black holes in the final stages before merger is measured in years, not milliseconds, but a space-based gravitational wave observatory, with arm lengths measured in millions of kilometers, sensitive to the extremely low frequencies produced by supermassive black hole mergers, is already being designed. The LISA mission, the Laser Interferometer Space Antenna, has been approved by the European Space Agency and is expected to open this observing window within the next decade or two, not in time to detect the Andromeda Milky Way black hole merger, which will not happen for billions of years, but in time to detect S-Miller mergers happening throughout the observable universe, which are occurring continuously as galaxy mergers proceed across cosmic history. Pulsar timing arrays, networks of precisely timed pulsars used to detect gravitational waves through the effects the waves have on the arrival times of pulsar signals at Earth, have, in recent years, found tentative evidence for a gravitational wave background at these low frequencies, consistent with what would be expected from the combined signal of many supermassive black hole mergers happening throughout the universe. The signal is not yet characterized well enough to identify individual merging cyst (MS), but its detection suggests that the universe is indeed full of merging black hole pairs, the long-term products of galaxy mergers like the one that may await our own Milky Way. What that technology would reveal, not just about the Andromeda merger, but about supermassive black hole mergers throughout the observable universe, and the deep connection between galaxy mergers and the growth of the most massive objects in existence, is a story about both the future of gravitational wave astronomy and the fundamental question of how the largest black holes in the universe got as large as they are. That is a story for another time. We started with a faint smudge visible on a clear night in the constellation Andromeda, 1 trillion stars, 5 million light-years away, moving toward us at approximately 110 kilometers per second. A fact known since 1912, when Vesto Slipher measured the B-Lu shift of Andromeda's light at the Lowell Observatory in Flagstaff, Arizona, and found it approaching at around 300 kilometers per second relative to the solar system. A correction for the Sun's own orbital velocity around the Milky Way brings that to about 110 kilometers per second in the galaxy-to-galaxy frame. Then, we followed what it took to turn that simple fact into a prediction. The need to measure not just the approach speed, that radial velocity, which spectroscopy gives us relatively easily, but the sideways motion, the transverse velocity, which requires measuring the apparent drift of Andromeda's stars against the background sky in microarcseconds per year. The extraordinary difficulty of that measurement at these distances, at which even the most massive galaxy is so far away that its angular motion across a decade is a fraction of a millionth of the apparent width of a full moon. The Gaia satellite achieving precision that no earlier instrument could match, and producing measurements précis enough to reveal, for the first time, how sensitively the outcome depends on a number still uncertain. 2 within tens of kilometers per second. The history of this measurement has its own arc. The first real constraint on Andromeda's transverse velocity came from Hubble Space Telescope measurements, accumulated over a decade of careful monitoring, which found a transverse speed consistent with a Rayleigh head on approach, and led to the 2012 paper concluding that merger was likely. Gaia, launched in 2013, was designed for astrometric precision far exceeding Hubble's, and as its data accumulated and was released, it offered a new and independent mesurement of Andromeda's proper motion, one that, depending on which systematic corrections were applied, pointed to a somewhat different picture. The Sawala paper used one version of the Gaia proper motion and found a 50% merger probability. The Wu paper ed a corrected version and found 90%. Both are using the same satellite. Both are using the same basic physical framework. The disagreement between them is not about whether the physics is correct. It is about a correction factor of a few microarcseconds per year, whose exact value is still being worked out. We saw a June 2025 Nature Astronomy paper put the merger probability at approximately 50%. A result that shocked many who had assumed the collision was settled science. And that represented a genuine and important contribution to the question of N for those who ultimately dispute its conclusion. We saw a March 2026 counter paper use corrected Gaia measurements to restore the probability to 90%, finding that the key difference was a systematic offset in the Gaia data that Sawala's team had not accounted for. We saw that both papers agree on the underlying problem. The measurement is not yet precise enough to be definitive, and current precision spans a range of outcomes that includes near certainty of merger and meaningful possibility of a wide pass. And we ended with the larger picture. A galaxy in motion, on a trajectory shaped by billions of years of gravitational interactions, heading toward a future that is more uncertain. And more interesting than any settled story about it would suggest. The transverse velocity of Andromeda is not yet measured with sufficient precision to definitively predict whether a merger will occur. Current uncertainty spans from about 65 to 100% merger probability, depending on which proper motion measurement is adopted and which systematic corrections are applied. Future Gaia data releases and dedicated Hubble proper motion campaigns are expected to improve this. But whether any forthcoming dataset will narrow the uncertainty below the threshold needed for a definitive conclusion remains to be seen. Wu's team estimate that reaching a decisive constraint would require proper motion uncertainty below about 2 microarcseconds per year per component, roughly 4 times better than the current precision of about 8 microarcseconds per year. The mass of the Milky Way's dark matter halo remains uncertain, within a factor of roughly 2, which contributes significantly to the range of predicted merger outcomes and cannot be resolved by proper motion measurements alone. The detailed role of the Large Magellanic Cloud in modifying both the effective trajectory of the Milky Way's center and the dynamics of the LMC M33 Milky Way system in future interaction scenarios is an active area of research. The LMC's infall is ongoing, and its effects on the Milky Way's dark matter halo continue to evolve, which means the gravitational landscape within which the Andromeda encounter will unfold is itself still changing. And the question of what the actual night sky would look like from Earth's solar system at various stages of the approach, assuming Earth still exists and a merger occurs, has not been precisely calculated for the updated orbital parameters from the 2025 and 2026 papers. The simulations that have addressed this question were based on older trajectory assumptions, and updating them for the current measurement situation is a natural next step. First, a fact known for over a century can still have significant uncertainty attached to it. We have known Andromeda is approaching since 1912. We did not know, until very recently, how uncertain its specific trajectory actually was, how much sideways motion accompanied the approach, and how sensitive the eventual outcome is to that number. Second, adding more precision to a measurement does not always reduce uncertainty, at least not immediately. Gaia produced more precise measurements of Andromeda's proper motion than any previous instrument, and those measurements revealed a dependence on systematic corrections that introduced new uncertainty about which value to trust. More data at this frontier revealed that the question was harder than it appeared. Third, the influence of objects not directly involved in a simple two-body interaction can dominate the outcome. The large Magellanic Cloud is not colliding with Andromeda, but its orbit around the Milky Way and the reflex motion it induces in the Milky Way's center may be among the deciding factors in whether the Andromeda collision occurs at all. The universe is not a collection of isolated two-body problems. Fourth, productive scientific disagreement between well-conducted studies using the same data source is not a sign that science is broken. It is a sign that a measurement is at the frontier of current precision, and that the question is genuinely hard. The fact that Sawala and Wu reached different conclusions from the same Gaia data, and that both conclusions remain defensible pending more precise measurements, is exactly how science at the frontier is supposed to look. Fifth, the appropriate response to genuine uncertainty is neither to pretend certainty exists, nor to conclude that nothing can be known. The current best estimate is somewhere between 65 and 100% probability of merger, with a median timeline of around 5 billion years in Wu's framework if it occurs. That is a meaningful constraint, not a useless one, and it will improve as the measurements improve. Uncertainty has a size. In this CAS, we know its size fairly well. That is itself scientific progress. If the fate of our own galaxy is currently uncertain, to within a meaningful factor in probability, somewhere between a near-sure thing and a coin flip, depending on which systematic correction is correct. What does that suggest about how confident we should be in predictions about the long-term future of any large system, cosmic or otherwise? The merger, if it occurs, will unfold over a period measured in billions of years. No human will observe more than an infinitesimal fraction of it. What does it mean to think seriously about an event on that timescale, and why does it matter to understand it at all? And looking up at that faint smudge in the constellation Andromeda on a clear night, knowing everything about what it is and where it might be going, the mass of 1 trillion stars, the uncertainty in a proper motion measurement, the ongoing work of researchers in Helsinki and Beijing and elsewhere, who are trying to answer a question that may not be fully answerable in their lifetimes. Does that change what you see when you look at it? If this one stayed with you, let us know which part landed hardest. Was it the measurement dispute between the two papers and what it reveals about the frontier of precision astronomy? The physics of what a galaxy merger actually involves for individual stars and solar systems? The role of the Large Magellanic Cloud in potentially redirecting the fate of two galaxies 1,000 times its mass? Or the final picture of our galaxy as a temporary configuration on its way to becoming something unrecognizable over a timescale that dwarfs everything we know? And if you want more of this, real science at the frontier of what we know, told with the uncertainty intact and the recent results actually covered, subscribe to Galaxy Pulse. And we will see you in the next 2 trillion stars, 2 dark matter halos, 1 measurement uncertain, 2 within 30 kilometers per second. Somewhere in that uncertainty, the future of the night sky is hiding. We are getting closer to finding it, just not as quickly as Andromeda is getting closer to us.